Alright, so basically transition elements are often referred to as the d block elements. Their outermost electrons are in the d orbital. So here is a graphical representation of the d block elements, right, and all other elements of the periodic table. So we have the s block element, we have the p block element, we have the d block element here. So basically we have scandium here. So scandium is 21 electrons. So Sc 21 electrons. So basically the configuration is Ar, which is 18 electrons, 4s2 and 3d1, right? So the outermost electron is on the d orbital, that is 3d. So let's look also at zinc. Zinc is basically 30 electrons. So the configuration is that Ar 18, 4s2 and 3d10. So this is basically 18 plus 2 plus 10 electrons. That gives 30 electrons. So basically d orbital is characterized by having L value of 2. So these are different orbitals. We have the S, we have the P, we have the D and F. So the L values are simply 0, 1, 2 and 3, right? So S orbital can accommodate 2 electrons, this and this. P orbital can accommodate 3 electrons, which is this. 6 electrons rather. And D orbital can accommodate 10 electrons, singly first, and then you pair up, right? So we have these electrons. So F orbital can accommodate 14 electrons. It's divided into 7 compartments. So 7 compartments. So for an isolated d block atom, so d block atom, let's say we have Fe atom or we have Cu atom. For an isolated d block atom that is not attached to a ligand, or it can also be ions like this, right? So their d orbital are degenerate. So this is a degenerate d orbital, 5 electrons, 5 compartments, right? So all the orbital here, we can call this dx, dyz, dxy, and all of that. So basically, let's put it there, dx square, dx minus y square. So basically, all the orbitals here are degenerate. They have the same energy. So this is peculiar to d block atom or ions that are not attached to ligand. So and electrons occupy them singly first before you start to pair up. So for example, we have Fe2 plus. So iron is 26, right? And the configuration is Ar 4s2 3d 3d6. This for this rather. So but when you lose 2 electrons, it becomes Ar. So the 2 electrons are being lost here, not here. So it becomes 4s0 and then 3d6, right? So the configuration therefore is going to be 1, 2, 3, 4, 5, and 6. So this is it, right? So d orbital for transition metal complex. So however, for complexes which is a combination of metal and the ligand, the d orbital are split depending on the coordination number of the ligand and the strength. So unlike for free atoms or ions of transition metal where the d orbital are degenerate, right? For complexes, they are not degenerated. They are not degenerate rather, but they are splitted. So there's a pattern to which they are splitted. So what determines the splitting pattern actually? So one is the coordination number of the ligand. So let's say we have 6 ligands here. That's going to give an octahedral crystal field, right? And when it's 4, it's going to give a tetrahedral crystal field. So another reason is the strength of the ligand. So the type of ligand here determines how the splitting will be. So it could be weak field ligand or a strong field ligand. So when the surrounding ligand is 6, it's octahedral. When it's 4, it's tetrahedral, right? So for example, let's say we have 4 moles of ammonia coordinated to cobalt here. So cobalt is 27 electrons, right? So but for you to know the number of electrons of the cobalt ion here, you need to first of all calculate the oxidation number of cobalt. So cobalt is CO plus 4. Ammonia here is a molecule, so it's 0. So we have plus 3, right? So we have CO and we have equals to plus 3. So therefore it's CO3 plus in this case. So we also have this one, right, as tetrahedral crystal field. Because the number of ligand is 4, here is 4. So they are tetrahedral crystal field. So tetrahedral, it's important to note this part, please. Kindly note these two parts. So tetrahedral crystal field has its d orbital split into this E and T2. So basically, for free transition atom, all their orbital, their d orbital are degenerate, right? But when they are coordinated to ligand, they become splitted. So we have this to be E and then T2 and then T2 rather. So we have E and we have T2. So this is T2 and this is E, right? So that's that. Another thing is that the tetrahedral crystal field gives I spin always, like I spin. What we mean by I spin is that the distance between this splitted part of this, this is like it's split into two ways, right? So there's a part here, there's a part there. So basically the distance between this is very, very small. So and because of that, electrons fill in singly first, like it always leads to I spin because electrons fill into it singly first before pairing takes place. So please take note of that. So let's look at this example. So we have cobalt Cl4 2 minus. So basically cobalt is 27. So let's calculate the oxidation number of cobalt here. We have it to be CO plus 4 minus 1 to give minus 2. So we have CO minus 4 equals to minus 2, right? So we have CO to be 4 minus 2 and that's plus 2. So the configuration is going to be CO2 plus and that will be AR, put in brackets. We have 4s. 4s. Let's write for CO first. So CO is 27, right? The AR 4s2, right? And 3d7. So but when it loses 2 electrons, it loses it from here. So we have it to be 4s0 and then 3d7. So the configuration is going to be, since this is 4, right? It's tetrahedral. So it's going to be this. So we have energy A. So 1, 2, 3, 4, 5. And then we're going to give this, and this to be this and this. So this is EG. Sorry, this has no G rather. Don't put any G there, sorry. So because it's not symmetrical. So this is E and then this is T2, right? So this is going to be, we're going to fill 7 electrons. That'll be 1, 2, 3, 4, 5, 6, 7. But here, when it's splitted, it's going to be 1, 2, 3, 4, 5, 6, 7. So because tetrahedral will always give a I spin, so we don't need to pair before we fill A. We have to fill everything first before we pair because the distance between this is very, very small. It's very, very small, right? So we have that. So when the metal ions are surrounded by 6 ligands, they have octahedral crystal field. So here is an example. So let's put this 2 plus Fe2, that's 2 plus A. So the ligand A is 6. So it's octahedral crystal field, right? So also this one has an octahedral crystal field, even though it's En. So En is bidentate. So it's 2 times 3 is 6. So the ligand has a coordination number of 6. So everything here is octahedral crystal field. So looking at this nickel, so if we have to calculate the oxidation number of nickel, it's going to be N plus 6 into 0 because it's a molecule, and therefore we have plus 2. So we have Ni equals to plus 2, and that's basically Ni 2 plus. So nickel itself is 28 electrons, and that's Ar 4s2 and then 3d8, right? This 10, this 20 and 28. But this becomes Ar 4x0 because you're losing 2 electrons. This is where you lose 2 electrons before s, right? And then we'll now have 3d8. 8, right? If you are losing 3 electrons, you lose from here first before you start losing from here. So basically the configuration is going to be 1, 2, 3, 4, 5, right? So put this energy. So the next thing is this. Now take note of this. Octahedral is inverted form of tetrahedral. So basically we're going to have this. We are going to have 3 here. So this is T2G and this is EG. First of all, it's different from tetrahedral. Tetrahedral has E at the bottom and T2 at the top. But this one has T2G at the bottom and EG at the top. And it's important to also note that there's G here, meaning that octahedral crystal field are symmetrical, right? But let's leave that for now. So we have 8 electrons. 1, 2, 3, 4, 5, 6, 7, 8. That's going to be. Now you need to take note of this. Octahedral can split in 2 ways. We are still going to explain that down below. But octahedral can either be high spin or it can be low spin. Low spin. You know, in the case of tetrahedral, we said the distance here is small, right? We said the distance here is small, and so because of that, we filled singly first before we start to pair in tetrahedral. But in octahedral, the distance depends on the type of ligand that we are using. If you are using a strong field ligand, the distance will be high, and therefore you have to fill this one completely first before you pair it, before you start filling this. Like you may have to first fill this one this way, then you pair before you start filling in the case of strong field ligand. But for a weak field ligand, H2O is a weak field ligand. Don't worry, we're going to talk about that in later down this video. So H2O is a weak field ligand, and because of that, we fill just like in tetrahedral cases. So we fill single first, we are filling in 8 electrons. So 2, 3, 4, 5, 6, 7, 8. That is the configuration of them. So let's look at the second. So here is the second reason. So we have the strength of the ligand. Now it's important to note that unlike the splitting pattern in tetrahedral, so tetrahedral we have basically we have it to be E at the bottom and T2 at the top. T2 and E for tetrahedral, right? But for octahedral we have it to be 3 and we have this to be 2, right? So now it's important to note that unlike the splitting in tetrahedral that gives high spin always, the splitting in tetrahedral can give either high spin or low spin, but depending on the strength of the ligand. So now we have 2 types of ligand strength. We have the weak field ligand and we have the strong field ligand. So weak field ligand, when you see halogens like chlorine, bromine, iodine, fluorine coordinated to the transition meter, just know that this is a weak field ligand, and the splitting pattern, like the distance here, will be what? Will be small. So it's going to give a high field. Like if it's a weak field, let's put it weak field light. So it's going to give high spin because the distance will be small. The distance will be small. But if it's if it's a strong one, we're going to come down to that. So let's look at this weak field first. They give a low splitting pattern resulting in high spin complexes. So here is an example that we just did. So you know it's Ni2 plus and it's TDD8, right? So it's going to be this octahedral is T2G and EG. So T2G and we have EG. So it's going to be 8 electrons. 1, 2, 3, 4, 5, 6, 7, 8. No, this is a weak field ligand. No, chlorine, bromine, iodine, fluorine, or sulfur, or oxygen. When you don't know atom is oxygen, as in the case of H2O here. So it's a weak field ligand, right? So now when we talk of a strong field ligand, strong field ligand have they have ligands. They are ligands with donor atoms like chlorine, nitrogen. So we have CO. This CO is a strong field ligand, or CN is a strong field ligand. They give a high splitting gap, resulting in low spin, right? So in this configuration, iron is 26. So but let's calculate the oxidation number here. So we have plus 6 minus 1 equals to minus 3. So we have it to be F minus 6 equals to minus 3. We have F equals to 6 minus 3. That gives us plus 3. So Fe3 plus has a configuration of what? That's a configuration of AR. We have 4s. No, let's start with this. This one has a configuration of Fe. F is basically AR 4s2 and 3d6, right? So for this, that's lost 3 electrons. So it's going to be 0, and this one will be 3d5, right? So the configuration will be, let's manage the space. So it's going to be this 1, 2, and here it's going to be 1, 2, 3. So we have T2G and we have EG. So the 5 electrons is going to be 1, 2, 3. Now take note, because this is CN, it's a strong field ligand. So it has the distance here is large. So we have to fill this first before coming up here. So we have 3, 4, and 5. So this is the arrangement of electrons. So now let's consider the arrangement of different number of electrons occupying the d orbital in an octahedral crystal field. So basically tetrahedral, we say that it's always high spin, right? And we also say that it's E to T2, right? So that's basically, we have 3 electrons here, and we have this to be 2, right? So for D1 is going to be this, for D2 is this, for, let's put it here, E and T2. So for D3 is going to come here, not pairing here, because high spin, the distance is small. So it's going to be 3, 4, 5. So D6 will be this, D7, D8, D9, and D10. So that's that. So for high spin, basically, octahedral can be high spin and can be low spin. So let's start with the high spin. So it's going to be is inverted form of this. So we're going to have this 3A, right? And then we have this 2A. So this is EG. We have to put G there to show that it's symmetrical. So we have this A. So D1 will be 1 electron. This is high spin. D2 will be 2 electrons, 3 electrons. So high spin, where the ligand is like this oxygen, donor atom, or halogens, right? These are the ligands there. So we have it to be 3. D4 will be this, D5, D6, D7, D8, D9, and D10. But for a low spin, the ligand basically are always strong field ligand, like CN, like CO, right? So we have this to be this, and then we have this to be this. So we have this to be D1 will be this, D2 will be this, D3. So D4 will not move here because the distance here is I. So D4, D5, D6, D7, D8, D9, and D10. So basically the conclusion is that tetrahedral crystal field, they have a high spin only because the distance, the splitting distance is very, very small, right? So you fill everything first before you start to pair. So but for an octahedral, a high spin octahedral can be high spin or low spin, right? Can be high spin or can be low spin. So it's high spin if the ligand is a weak field ligand, and its examples are like the donor atom of O in oxygen, in water molecule, when we have halogens like C, bromine, iodine, fluorine, and all of that coordinated to the to the transition metal. So for a low spin, we have this to be CN and CO, and they are low spin because they are strong field ligand. The splitting distance is I. So thank you.